I don't need to do one, right? Do I need to do two? Oh, two is actually not easy, man. Yeah. Wow. Two is not easy. Um, they ask you for the average speed of the whole flight, right? How would you do two, man?
I just like assume like if my 600 km back and forth.
Yeah, yeah. So then you went to find total distance, right? Yeah. So I guess for question two, you would have to question two, you probably have to oh sorry. Hang on.
Yeah, possibly a lot. I have no idea.
Yeah, okay. So so question two, you probably have to find assume 600 km distance, and then after that find the total time taken, which is 1 hour, right?
Yeah.
Yeah, 600 km. When it's on the return flight, 400 km per hour, how long would it take? 1.5 hours, right? So 600 km plus 600 km, but then the total time is 2.5 hours. 2.5 hours. So 1,200 divided by 2.5, right?
Yeah, so
You get 480? 1,200 1,200 divided by 2.5. Then you get 480 km per hour. So yeah, C's answer. Okay, yeah, there you go. So question two, C. Three. Do I need to cover three? Do I need to tackle three? Anyway, I'm doing this debrief not because I want to check your marks or anything like that. Is to check your concepts for tomorrow. You know what I'm saying? Like maybe there's some concepts you got mixed up on or something like that. So we kind of like need to know the concepts for tomorrow. So it's not about the scores. I mean at this point I don't really care about the scores. I care more about the concepts. Do I need to cover three? Ryan or Cassandra online? No? I think this one here is D's answer. Yeah, this one's very straightforward. D's answer. Sorry. Original length. Original length of the spring. Do we need this? So this one is F equals to kx. F is to kx. But then for this one here is the total length is 0.55 means which means what? X plus L naught, right? So 0.55 equals X plus L naught, which is the original length. Yeah. So 25. If you hung a weight of 25, it would have stretched, right? Based on the equation, it would have stretched for 150 times x. Yeah, that would have been the extension, right? So you need to put x inside here and then find L naught. Okay? Also not too difficult, right? This one? Okay. That's the equation for that one. But this one though, wow. This one. What's the density of oil versus the density of water? Damn. Okay. So whoever was doing this workings here, right? I think one of the things I want to comment on would be like you know, yes, the forces, but we're missing one force. You're missing the upthrust force, right? The upthrust. Okay. Rho Vg, water has a greater density than oil. I would expect the upthrust of water to be higher. Okay, so I would expect the upthrust to be bigger. And that said, that therefore the tension in the water will be less. Okay, so it's kind of like TW, right? Plus UW equals to, I would use mg. I wouldn't use W, right? I would use mg. That's my habit lah. I'd rather use mg than W because sometimes it'd be easier. So then T oil plus U oil equals to mg again. But they want you to compare the density of oil to the density of water. All right, so which means that you have to okay, well, TW is just P, isn't it? Yeah, TW is P. P is less, huh? So the whole idea is that this is a Newton meter. So when you pull it down, P goes to Q. Q is a bigger value, right? So which is basically what I'm saying. So this is P plus rho W V of the object, G equals to mg, and this one is Q plus rho oil, Vg equals to mg. Okay, so we sort of have a semblance of something happening already. We probably can equate the two sides, right? So P plus rho W Vg equals to Q plus rho oil Vg. Right? If you rearrange it, you will get what? Seems like something is missing.
No, you just need to put like the two equations in terms of P W and P O. And then you P over P W. Yeah, right. I tried that. I don't think it works.
Oh yeah, I will be stuck, right?
Yeah,
So
like rho W equals to mg minus P over Vg. And then rho oil equals to mg minus
okay. The mg, the w must be still there, lah. Okay, so that's annoying. Okay. Oh, I see. So you can't do this, yeah. So that means, yeah. Oh, so you have to backtrack one step, and then I had to backtrack one step and make rho w the subject, which is w minus p over vg, and w minus q over vg. Then divide this one by this one. The vg cancels off. So it's basically W minus Q over W minus P.
Yeah.
D. Yeah, D's answer. Okay, that's 5. Next one. What's the ratio of GPE gained by the car over work done by the force? Wow, these are tricky questions, huh? So H, right? H is S sine alpha. So the GPE gained by the car will be mg S sine alpha over what's the work done by force F? Work done by force F. Yeah, it's just F times S, right? F times S. So the S should cancel off. And for D's answer, yeah, okay, right, that's fine. Okay, no issues there. Oh gosh, okay, you know what? Let me just find something that I need to do then. So a lot of it is just trying to go through the motion, right? So this one I don't need to do this angular acceleration, right? Okay. How about number 8? Do I need to do number 8? Okay, let's see. Let's do number 8. So this K had a certain angular momentum at first, which is IA omega A. Am I right? IA omega A, that was the initial angular momentum. And then they put this B drop onto this A, right? Which means that, yeah, but you see the total angular momentum is still going to be IA omega A, right? They did say that the both objects will have the same angular speed of omega. So IA omega A is basically IA plus IB omega, right? And they're asking what is the ratio of omega over omega A, which in the way I see will be IA over IA plus IB. Is that right? And then they did give us a ratio of IB to IA. IA is basically 4 times that of IB, right? So I can just write this as, I guess, 4 times of IB over 4 times of IB plus IB, whoops, right? Whoever this is, 4 over 5. C's answer. Yeah. All right, so this one here, C's answer. Okay. I think maybe careless mistake, man. Not too sure. But I'm seeing a kind of weird stuffs here. I'm seeing kind of weird workings here. So, I mean, whoever it is, I'm not too sure what's going on. Seems like we've gone down the wrong track. All right. So the way to do this question is to equate the angular momentum. So you have your angular momentum here, and then you have your angular momentum is the same. So when you add the when you add the two objects, their moment of inertia just adds up IA, IB, and then final angular momentum like this. So then the ratio they want is right. So omega over omega A equals IA over IA plus IB. Then you use their ratio and then just submit it. Right. So yeah. What's up? Why was there this square thing here going on? What's up with the square thing? We need to figure out what went wrong here, because that tells me it's a little bit of a wrong concept there. Okay, right? So we need to fix that wrong concept. But anyway, this is A4. Yeah, so A4 is I didn't really, did I not really? I didn't really, have I revised A4? Have I really?
I don't think so. Yeah.
Was it half a lesson or one lesson?
Yeah, actually, wow.
I think it was like half a lesson though. Yeah, probably we'll have to do a bit more practices. Well, whoever it is, right? I mean, whatever it is, guys, if you realize that this is a bit, I mean, I'm seeing some conceptual errors here, right? Keep track of it. Let me know that you need help for it. Or maybe you can refer to the videos. But even after watching the videos, you're still getting it wrong, let me know. Then I'll just, make plans to revise for it. Okay, so that's for 8. Why can't they just hold a physics exam next week? Why do they have to? Next week is what? Honors week, is it?
Honestly,
Honors day, right? That's why they have to do the celebration and all that. Okay, that's just annoying, man.
I think Monday is bio.
Okay, number 9. Number 9. What's this? Yo, what the shit? So you have a whoa. Okay, okay. I mean, I wouldn't have thought of this, but okay, fine. Okay, so the original cube is x by x by x, or 1.5 meter by 1.5 meter by 1.5 meter. All right. So this one here is just straight up length contraction, but the whole idea of length contraction is only in the dimension that he is traveling in, which means that to the space traveler it will look like this. Right, so it'll be 1.5 meter, 1.5 meter, and then the contracted length. Yeah. So you have to go and find out what's the contracted length, and then use that new contracted length to find that volume. Yeah, this is that annoying, but I mean, okay, like interesting. I mean, crafty, but yeah. Okay, so the length contraction only happens in the dimension that the relative to the dimension that the traveler is traveling in. Right, everything else will look, the other two dimensions will look normal to him. Damn it. What's the answer for this one, by the way?
Yeah.
Right, A is the answer, is it? Oh, okay. Right, so you have to go and find the gamma factor, and after you find the gamma factor, you have to do length contraction, so L over L naught over gamma, right? And then you can find your L there. We okay at this? Yeah? Yeah, there you go. I'll save this document and send it out. I guess this is this do I should I okay, what's question 1 answer again? Let me just do a C. Answer is C. Okay, then 2 is C, 3 is D, right? 4 is what? 4 is A, is it? Okay, 4 is A. I didn't show the working. 4, this one is D, this one is D. Angular acceleration of the wheels, number 7 is what? What's that? A, is it? Okay, 7 is A. This one is C, this one is A. Okay, this one here, number 10. Now, number 10 is super long. Number 10 actually turns out to be very, very long working. I don't know whether I'm just overthinking it or overdoing it. But I did show out the working the other day, right? This is a freaking annoying question. Turns out, I think, right, I'm guessing, right? Okay, to be honest, this question comes from a textbook. I don't think it came from IB before. But if IB comes up with this, right, then that means that there's a standard formula for effective thermal conductivity, then it's just D. Yeah, that means, you know, you treat it like parallel resistors, you know what I mean? Like, yeah, you treat it like parallel resistors. So when the current is when the uh, heat is conducted through both of them, right? So it's just D then. Okay, so 10 is D. All right, what's the next one? Next one, 11 is it? Okay, so 11 here is we have to kind of like just take a look at this. Okay, so the top layer makes sense. Incoming 340, reflected is 100, outgoing is 240, right? Outgoing is 240. All right. Surface radiating out is 390, right? But you see, right, this 390 is essentially a combination of the surface 240 plus the radiated by atmosphere, right, amount, which is the difference, right? So isn't that just 150? It's 150, right? 150. So when this thing goes out, when it tries to go out, the atmosphere absorbs 150 of it. That's why the outgoing eventually is 240. But then the 150 is then re-radiated back again. Okay? Yeah. This is just a very simplified model. Obviously, the atmosphere should radiate out in all directions, right? Not just absorb one direction and then radiate this direction. Yeah, but I guess this is more. So B is the answer for this one. Okay? All right. 12 is interesting. I was looking at 12 last night. No, yeah, someone sent me a picture of this last night and was wondering how to do this. So, got to remember that for these kind of questions, the first principle is that the pressure is the same, right? So they have the same pressure. So this guy has the same pressure as this one. Okay. So PV equals nRT, PV equals nRT, right? The volume of Y is twice of that of X. So we're gonna write P V equals to N, right? I don't like the big letter N, right? It's supposed to be small letter N, but okay, right? N R, or you can put NKT if you want. Well, number of molecules N, right? So you know, technically speaking, I should put in NKBT, right? So that would make sense. Then this is 300 kelvins. They're not trying to be tricky. They gave me in kelvins, and therefore the other one is what? Same P, but this time around is 2V over no, I mean equals to 3N, then KB, and then the T is unknown, right? So all you have to do is just compare the two equations, compare the coefficients, and then get the temperature. What am I looking at? 200? 200 kelvins, yeah, 200 kelvins, yeah, there you go. Right, so that's for 12. 13, do I need to do 13? 13, so what the heck is 13? 13 is not even a cycle, man. Right? Right, look at this. This is not even a cycle. The triangle goes here, triangle goes, I mean, the process goes here, goes there, right? Then this process goes here, goes there. It's not about, it's it's not about a cycle. It's about which path is more efficient or something like that.
No, it's just
Oh no, no, you're just supposed to figure it out. Okay. So, oh, this is an A level question, man. Sorry. Yeah, this is an A level question. I've done this before. Huh?
syllabus.
This is syllabus, but it's an A level style kind of question, right? But honestly, I think that they can do that lah, because thermodynamics are like that. 8 joules of energy from PR and RQ. 8 joules is absorbed, and 3 joules of work is done by the gas. So PR and RQ is it?
Yeah.
So this one here is the Q is equals to 8 joules. The W is equals to 3 joules. So the change in internal energy from P to Q, change in internal energy from P to Q is 8 minus 3, right? 5, right? 5 joules, right? Okay, so that's the change in internal energy. So when the same resultant change is taken by P to S and S to Q, only 1 joule of work done. So this one here from this way, that will be 1 joule. The W is equal to 1 joule. W is equal to 1 joule. And therefore the 5 joules, because it's PQ, is equal to Q minus 1. So Q is equals to 6, right? So B is answer. Okay, B is answer, right? Because 6 joules is absorbed. So you gotta do it this way. You gotta find out what's the change in internal energy from P to Q. Right, that's for 13. Oh, these are all one-hit wonders, huh? So like they only have like one. There's only enough space for like one question per chapter, right? Okay. So we're on B5 now. This one here. This one, pretty sure we did this somewhere, right? If you're not good at this, what do? If you're not good at this, you gotta fight the urge not to draw it, and that means we have to draw it. Okay, you have to draw it. Okay, and then you gotta really tell yourself, you gotta remind yourself that this voltmeter here, right, the voltmeter being placed across here is the same as placing the voltmeter across here, right? You gotta be able to tell that, right? So there you go. Yeah. Okay, right, and this one's what, 6 ohms, 6 ohms. So the total resistance for this combo here is what, 3 ohms. So you have a 3 ohm to 1 ohm split between 12 volts. So how many volts is that, like, in total here? So this is 12 volts, right? What? So 9 volts and 3 volts, right? So 9 volts is your answer, right? So 14. Okay, 15. I heard someone say about what the internal resistance graph. Okay, I guess not you guys. Probably someone else. Huh? Oh, really? Oh, shoot. Do I have 1B here? Do I have one B here? Oh, no, no. Oh, okay. Nobody took back the 1B. Okay, right. Then, okay. Okay, let's look at this one then. So that's where the internal resistance questions was. I was like wondering who was talking about this. Okay. What's the TPD of the cell? Wow, what's the TPD of the cell? Right. So, I mean, did I do a revision for B5? Did I? Oh man, okay. Well, what do I say about TPD? What's our layman's understanding of TPD? Our layman's understanding of TPD would be um, it is the voltage given to all external resistors, right? External resistors, which means what's the voltage given to the 10 ohm guy, right? So we got a 3 volt battery. There's an internal resistance of 2 ohms. This one's 10 ohms. So, how much volts does the 10 ohm get? That's the TPD. Isn't it? Yeah? Oh, that's a weird thing. 10 over 12 times 3. Right? So 10 over 12 times 3. That would be what? 2.5 volts. Sorry, the math is not working for me. But yeah, okay, 2.5. So 15 is C. 16. 16, let's look at 16. What's that 16? What are initial and final voltmeter readings when the variable resistor is increased from 0 to a final resistance of R? No. 0 voltmeters across the other guy. So when this is 0, all the voltage goes to him. 6 volts. When this is R, then the voltage is split evenly. 3 volt, 3 volts, 3 volts. So 6 and 3. 6 and 3. I got two options, 6 and 3, 6 and 3. Initial is what? Initial is 0, right? Increase from initial of 0. So C is answer. Okay, this one is, yeah, this one is that's just like that. 17. 17. Oh. Oh, so you double the amplitude, is it? You double the amplitude. That shouldn't change the period. Yeah, that shouldn't change the period. So it's either this or this. And then you have to do the equation though. Total energy. Total energy of your oscillating system is half m omega squared x naught squared. So if you double the amplitude, you will 4 times the total energy. Shit. No. No. Wait. Yes. Sorry. Yes. I thought they doubled the mass. Hey,
Exactly.
why they not doing double the mass? Yeah, why don't they double the mass? Why did they change the question to something so lame? Like, I mean, usually they'll double the mass. Because when you double the mass, right? When you double the mass, the m here is doubled, the omega is also affected. Yeah, if they double the mass, the m and the omega is affected because omega is 2 pi over m, 2 pi square root m over k, right? If you did that, then both factors, but they only doubled the amplitude. I'm like a bit confused myself. A is answer. Okay, 18 is what? Speed of water wave, is it? 10 hertz. Oh, F lambda, right?
Yeah.
Oh, that's so weird. This is in cm though. Yeah, that's right. That's in cm. 0.02, 0.2. Okay, A lah. Why they suddenly go easy on you guys? 19. Which of the following best describes wave speed of progressive wave traveling through a medium? What the? Okay, these just answer lah. That's it. That's all. Okay. Number 20. What's this? 20. So after, right? After they have passed through each other, right? So B lor. Okay. Yeah. No. Yeah. 21. What the? Why are they asking this? What? Okay, sine big over sine small would they try to be funny here. Sine Q over sine S. D's answer. Oh, they suddenly went easy again. Right? Yeah, they're becoming easy again. SLs were complaining that there was a diffraction grating question. Like not sure why also. Okay, which of the labeled lines gives you 2.5 lambda? 2.5 lambda. I mean, it's all based on the order number, right? The one in the middle is what? N equals to 0. Then this one here is n equals to 1, right? Then this one here is n equals to 2, right? Right, n equals to 2. So everything in between is like the 0.5, right? So this thing here is n equals to 2.5 lah. So that's what they want, right? 2.5. So 4 is the answer. Right? So, this thing here, you probably will have to review the C3, right? C3 video when I was actually doing like, this whole overlapping two waves thing, right? Yeah. I was doing this thing here. So that's 22. 23. 23. 23. Oh, 23, right? Don't get tricked, 23. They want for angular width. So this is a single slit. So single slit will look like that. Whoop. Right, single slit will look like this. Okay. Then you have the angle between the maxima and the first minima. That's theta, right? Okay, that's theta. But they want the angular width of the central maximum means that the angular width of the central maximum is 2 theta. This one here is 2 theta. Yeah, because then theta equals to lambda over b, so 2 lambda over b, A is your answer. Okay, that's 23. 24. 24. But 23 is A. 24. Oh, wow. Is it constant speed? Constant speed, constant frequency, passes by and stationary observer, which is here, this guy. All right. C is answer, right? This one here did it in C5, right? This first two graphs don't make sense. Why would the frequency be 0? Frequency 0 means here nothing. Then how do you get negative frequency, right? These two graphs are all wrong, right? So it's pretty much approaching higher frequency, switches over to low frequency. Like what was the original frequency? The original frequency is the midpoint here. Yeah, that was the original frequency. That's like the F naught, for example. Yeah. Okay, that's 24. 25. 25. Satellite orbits planet X with Vx from the center of the planet, V1 from the center of the planet. Mass of the planet is m. What the pong? But just orbital. It's just the orbital equation, right? Gm over r, right? Do they have the same r? They have the same r. So basically, just comparing v orbit of x over v orbit of y. right? Which is basically square root of G M over R over square root of G 4M over R. Is that right? Half?
Yeah.
Right, because square root of 4, right? Square root of 4 is 2, so it's just half. Half. B's answer. Oops. Okay, so there you go. What happened? Forgot to do the square root. Forgot the square root. Oh my god, I see it there. Ah! Forgot the square root. The square root disappeared. The square root of 4 is 2. Okay, that's 25. Okay, what's the next one? The great this question is a BIT, right? C. Okay, so greatest work done by the G force. This is the greatest work done by the field, right? If you remember the painful lessons that we went through in D1 and D2 at the start of the year, right? That was the thing that I was trying to emphasize, right? Like the work done, like all the what M del V, the M del V, that's work done, right? But that's work done by external agent, right? That's work done by external agent. This is also the change in GPE, right? But since they ask you by the work done by the field, work done by the field is like the opposite of it, right? So the field always tries to pull the mass when a mass moves from up. Always tries to pull a mass from an outer region to to an inner region. Okay, all right. So it's kind of like something like this would be the greatest work done already, right? Yeah, from Q to P. But you don't have the option. So the other option is from S to R to S.
Yes, sir.
R to S. Oh, you still don't have that as well.
R to P.
What's it what?
Before R to P.
What the tong lah? R to yeah. So it means you could okay. So annoying. So the work done from Q to P, from R to S, from Q to S, or from R to P, right? All them same. They're all the same. Work done, greatest work done. So you just choose one. Right? So like what you say, R to P, C is answer. So freaking annoying. Okay, yeah. So D1, if you're not familiar with this whole thing that I'm talking about, it's like, oh, what's this work done by external agent, work done by GP and all that, right? During D1, I explained it in such a way that there's three things that you have to watch out for, and whenever you see the question ask you work done by, oh, right, you realize it's not work done by external agent, it's work done by the G field. You have to flip it around. Yeah. So that's 26. 27. Oh, this is the exact thing I did in the revision, right? For E fields. But that was what? That was June. That was June. I say right at P, right? You gotta add both of them, right? Don't accidentally put a negative sign, right? Because I know there's a negative sign here like this. So the field from Q is pointing to the left, and the field from uh from negative 2Q is also pointing towards the left. So you basically have to make sure that you add both positive values in, right? Like I said, the danger is students use this equation, right? KQQ over x squared. Where's the square? There should be a square. Is the square missing? This one is also missing. Please don't be missing. I don't know whether is it missing. Oh, there's no option for it to be missing. Okay. So they should have, right? Okay, so K um QQ over X, that's E, right? And this is E.
It's KQ X.
Oh yeah, that's a force, sorry. KBQ, all right, KBQ over X squared, sorry. X squared. That's E. So the other one would be, I mean, that's E2 lah. E2 is equals to K2Q over 2X squared. So this works out to be what? Half, right? Half of E. So it's basically 1.5 E, right? Yeah, so E total equals to E plus half E. All right, so that's 3 over 2E, right? So it's 27C. Okay, next one. There's 40 questions, right? Or is it 30? 40, yeah, there's 40 questions. 28 is what? Holy crap. Oh, this, okay. Oh, okay. I mean, okay. What they're asking for? Voltage. All you have to figure out is what's the total voltage in the center, right? What's the total voltage in the center? So you just need to figure out one, isn't it? Yeah, you just need to figure out one. So you would reckon that this is D, this is D, D and D, right? So this one here will be square root of 2, square root of 2D, right? So the hypotenuse is square root of 2 times D, right? And the voltage of 1 will be KQ over square root of 2D. You can't get rid of the square root, it's there forever, right? Yeah, it's there forever. And then, yeah, this time 4, right? So V total will be equal to 4 times of KQ over square root of 2D. So you need to do the math. 4 divided by square root of 2 is 2 to 2. Is that right? Damn. Okay, yeah, a bit of math here. Hey, where's the calculator part at? How come I have not touched any calculators yet?
Yeah.
Huh?
Yeah, there's a lot.
So the I pass IB paper. Dang it. So yeah, you're supposed to be able to use your calculator up to some point, right? You are, yeah, you're given a calculator. So these are still past IB questions. Okay, 29. What's up to 29? So this is BQV equals MV squared over R, right? BQV equals to MV squared over R. Oh, strange. Mark Menon asked me this question the night before. Wow. So am I right to say that R equals to MV over BQ? Right? So what would you do? You would increase the mass to get a bigger radius. So C is your answer. All right, good. Let's go on. Next one, 30. Induced EMF. You halve the rotation though. You halve the rotation. If you halve the rotation, the peak also double. So C is your answer. This one is just straightforward. Right. Now what? Oh no. Sorry. Oh, I see wrongly. Right. All right. A is your answer. What? Because half the rotation. So the period is yeah. So period times 2. Oh man. All right. So now it's 40. Right. This is the original period. Yeah. So double whammy. Always remember this AC generator has the double whammy. That's 30. 30 is A. 31. Wow. What an ass, man. These people. So yeah. What an ass. Okay. So you know that the flux is BA cosine theta. That's the standard equation from the data booklet, right? But you know, this is like D4, right? So D4 I did it just before June. Haven't revised it yet, but we will revise it soon. But what's this theta supposed to be? This theta is supposed to be the angle between the flux and the normal to the surface. Like this would have been the flux. This theta would have been B and the normal of the surface. That would have been theta. But they didn't give you that theta. They gave you this theta instead. They gave you this angle here like this. So in a way, you can think of it as, since this is 90 minus theta, therefore the equation is NBA cosine 90 minus theta, which then makes it sine theta, isn't it? So B is your answer here. Yeah, B is your answer. Okay. What's another way of doing this? Another way of doing this is to resolve the vector into 2 parts. So you could have the vertical vector and the horizontal vector, right? And then after that, you can split it into 2 and realize that the component that you need is a component that's perpendicular to the area. So that will be the sine theta. So B sine theta, right? Yeah, there you go. So B's answer as well. 32, come. white light, okay, pass through sodium vapor viewed through a diffraction grating. I think this is where it was confusing for the SLs, because diffraction grating is not in the syllabus. So which means that the SL see this question, right, they'll be wondering what the heck does a diffraction grating do, right? But I did mention that during our lesson, I did mention that for SLs, you know what you use a prism. For HL, you use prism or diffraction grating, because the two of them will help you split the colors, right? Okay, so diffraction grating or the prism is also fine. Okay, yeah. But this is white light passing through sodium vapor. So you got white light, and then you got vapor here, right? And then whatever comes out of the remaining. So what happens inside here? So what happens inside the vapor? Yeah. So some photons are absorbed, right? Some photons of white light is absorbed. So what happens then? Some photons of white light is absorbed. What happens after that? So whatever is not absorbed, right? Remaining photons that are not absorbed. Remaining photons not absorbed. Okay? So that would be a dark lines on the color background. C would have been your answer. Dark lines on the color background. Okay? Right? Not white background, dark background. So C is your answer. Because the remaining photons not absorbed is actually a lot, right? You only absorb like what, 5 or 6 or 7 of them only, right? The rest of them are not absorbed. Okay, 33. Oh gosh. Okay. 2 to 1 produces wavelength of 440. Wavelength of 590 is also emitted. What is the wavelength of emission by the third transmission? Oh shit, okay, yeah. So there's 1, 2, and the whole thing 3, right? So they're saying 2 to 1 is 440, but then 590 is a lower energy transition, right? This is a lower energy transition. This is 3 to 2. This is 3 to 2. 3 to 2. Okay? Yeah, 3 to 2. Then they ask you what's the oh damn. Okay. So this is, wow. This is a hard question. This question is hard because you have to calculate. Oh, this is where your calculator comes in, guys. This is the first time you got to use a calculator. All right. So E2 to 1, right, will give you a wavelength of 440 nanometers, Hc over 440 nanometers. Okay. E3 to 2 will give you a wavelength of 590 nanometers. You have to recognize that 590 is lower energy than 2 to 1, which makes 3 to 2 even smaller energy, which is true. So whoever made a marking here, 590 is as well, right? But you got to recognize that it's Hc over 590 nanometers, 590 nanometers. And the total transition of 3 to 1 will be an addition of these two energies. Yeah. So this will be Hc over 590 nanometers plus Hc over 440 nanometers equals to Hc over lambda. Yeah, the unknown nanometer there, right? Anyway, if you can reduce to two options, it's either A or B. It cannot be C or D, right? I guess you just have to work this out. So 1 over 590 plus 1 over 440 equals to 1 over whatever lambda, and then you just do the flip over, and then you get 250. B's answer. Okay, there you go. So that's for 33. Damn. 34. UV intensity this. Wow, this is where all your calculators come in. Yeah, this is where all your calculators come in. What's the rate of photon per meter square? Rate of photons, right? I've taught you this in a one page here, right? In one page, I mentioned to you. What's the equation you have to write down? I didn't see the equation here. I hope you got it right. Right? Intensity is equals to N over T, HF over A. Right? I said that, right? So that's the thing. So it's 10 equals to N over T, Hc over lambda 280 times 10 to the power of minus 9 over 1 meter square, right? So you can use that and you can find n over t. Find n over t, that's it. Which is? A, yeah? Okay. So I'm assuming, yeah, A. And it looks at 35. 35. Look at that, they don't care, they just draw straight lines only, right? What? So your second EM radiation is shorter wavelength. Shorter wavelength means higher frequency. Higher frequency, right? Higher frequency. Higher intensity. Higher frequency, higher intensity. Right? What will be the changes of Imax and VS? Okay? We draw the graph lah. It should look like that.
Wait, the IMAX is like proportional to
Oh shit, wait.
yeah.
No shit. Oh my god, you have to calculate this shit. Oh my god, you have to calculate this shit out. Oh shit. Oh shit, this damn freaking annoying. Oh my god. Wait. Holy crap. So L is equals to N over T HC over lambda A. Right? The new intensity is 1.2. The L naught is this. 1.2 L naught equals to N over T HC over 0.7 lambda not over A. So you basically have to find out whether N over T ends up being bigger than the original rate, right? So you have to compare. You have to compare N naught over T and compare N yeah, T. Is that not just 1.2 times 0.7?
Yeah.
Which is how much?
0.8.
Damn! So N over T is 0.84 of N naught over T. This is a damn pain in the ass. So higher frequency will result in bigger VS, right? Will be more negative stopping potential, right? And therefore your graph will be bigger stopping potential. Let's check. Bigger stopping potential, but only 0.84 the rate of photons, so 0.84 the saturation current. Wow, these people are nasty, man. Okay, so it's something like that. This is your new graph. So anode stopping potential is more negative. Oh, I like it. I like it when they're a bit more clear like this. More negative. That makes it very obvious. Because when you say greater stopping potential, right? What do you mean by greater? Is the number greater what? More negative. I love it. Right? This is how A levels should be taught as well. But no, A levels are very vague one. Are you sure? You know, it's more negative. So what does it like? It's bigger. What does it mean by that? I hate it. The A level side is very passive aggressive one. Then you have your IMAX. IMAX is actually lesser. A is your answer. Yeah, this one here, lesser. Yeah. This is a hard question because you had to go and figure out what's the rate, what's the new rate. Oh. Okay, number 36. 36. Oh my gosh. These people are nasty. Wow, they became very nasty towards the back part, huh? E equals to P squared over 2m, right? De Broglie wavelength equals to H over P, so P equals to what? P equals to square root of 2me, correct? So H over square root of 2me, right? Then they say that you changed it such that the wavelength is now 4 times of lambda, which actually meant that you actually decreased it, no? Right? So yeah, because longer wavelength means lesser energy. Yeah, longer wavelength means smaller energy. Oh shit, this is not easy, man. My head is I have to write all this out. What? Okay. So basically, for lambda, equals to h over square root of 2me2. How about that? Yeah, yeah. And essentially, I just need to make the e's the subjects. No, no. Okay.
Yeah.
I want to find del e, right? So technically, I need to make e2 minus e, right? Let me try. Lambda squared equals to h squared over 2me. E is equals to h squared over lambda squared 2m. E2 is how much? E2 is how much? E2 will be h squared over 16 lambda squared 2m. Is that right?
Yeah.
Yeah? 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 And the difference will be E minus E2. No, the change, right? So it's either plus or minus, right? That's what I'm concerned with, right? Plus or minus. There should be a decrease in energy. There should be decrease in energy. So E2 minus E1, E2 minus E1. Damn. I mean, these last few questions are hard, okay? Right? It went easy for a while and then went up again. E2 minus E1. This will be 1 over 16 minus 1 E. Am I right? That makes it 15 D.
Yeah.
Yeah, negative 15 over 16 E. Oh, that was the change because the worst thing is they're asking for the change. They're not even asking for the final. If they ask you for the final, right, that's like the value is 1 over 16 E. But they're asking for the change, so you had to express both E1 and E2 and then you have to find the change. Damn. Okay, 37 is what? What? Oh my gosh. This is the exact thing in my notes. This is the transmutation of nitrogen. Transmutation. Okay? I mean, if anything, right, you can sort of guess the energy is absorbed lah. So it's either B or C now. Because of the exact example I did in my class, right? This transmutation, when you did the masses, the energy was actually supplied. So B or C. It's not liberated. It's not given off. Okay, anyway, so yeah, what do you have to do? You have to find total mass on both sides, right? Find the total mass on both sides, which is given also, right? So mass gain, right? Look at that, that's mass gain. So how much mass does it gain? 69 minus 57, 0.00. Wow, calculator coming out already. 69 minus 57, right? 0.0012 U. This is the mass gain. Mass gain is 0.0012 U. And then you can just multiply nitrogen 1.5, right? Yeah, but nitrogen 1.5, so no, 0.0012 times 931.5, it gives me 1.11, 1.12 absorb, C. There we go. Yeah, C. Then you multiply by 931.5 MeV. Okay, absorb, It's a mass gain, mass gain. There's a gain in mass. Yeah, gain in mass. Right, 38. 38. Wow, these people are nasty. These people are nasty, man. These people. Towards the end, they really make you work, man. Freak. Okay, A equals to lambda n. Oh gosh, you don't have lambda, so you need to convert your lambda into sorry, you need to convert your half-life into lambda. So T half equals to ln 2 over lambda. Okay, what am I doing? Lambda equals to ln 2 over T half lah. Okay, so lambda equals to ln 2 over T half, right? And therefore that's what? What's that? Do you work this out? What's that? Yeah, it's just basically ln 2 divided by 30, right?
No.
Yeah, don't worry. It's ln 2 divided by 30 first. So that's 0.023105 per year. That's the probability per year. Okay? But yeah, this is quite annoying because they ask you for activity of becquerels. And what's becquerels? Per second. So they're being nasty here, right? You can see that I did mention, right, that some teachers are just like, oh, right, I'll give you becquerels and see whether or not you know what to do with it, right? It's per second. So you need to convert this to per second. Ugh. Right? Or you can convert this to per year lah. if you want.
But they give the conversion.
Huh? Okay lah, okay lah, okay lah. So hang on. So if this probability per year is so low, per second is even lower, right? So it's 0.023105 divided by 3.15 times 10 to the power 7 per second. Is that right? Yeah? Yeah, per second. How much is that? 7.33
times 10 to the power.
times 10 to the power minus 10 per second. So that's a very low probability per second, but that's the decay constant multiplied to lambda, and you require this amount of Becquerels. So 1.85 times 10 to the power 5 is equals to 7.33 times 10. Hey, this one is called lazy already. Then this one, the fella just probably pulled it out from somewhere and then just expected the students to like, you know, do all so many steps. There's so many. We're not even done yet, no. Like, because after this, right, after we find a equals lambda n, after we find n, right, n is not even the n, not even the n yet. You asked me for mass, eh. So the next thing I need to do is I need to find out what's the mass of each cesium 137 atom also. So you have n here. What's n here? Well, these people are nasty, man. Nasty. 1.85 times 10 to the power 5. Okay. Then divided by 7.33 times 10 to the power minus 10. Alright, so why do I have a syntax error? Dang it. Do I have to put a bracket everywhere I go? Oh my gosh. So that's 2.524 times 10 to the power 14 particles, right? So then after that, I need to find the mass of each cesium, 137. So what's the mass of each cesium 137? 0.137 kg divided by 6.02 times 10 to the power 23. Or I did mention that if you are not very good at this mole concept thing, you can say 137U also, which is about the same as 137U. Yeah. So you could take, and then basically you just multiply it and get it in kg, right? So what's the answer finally?
C.
Is it C? All right. Okay. Yeah. Well, what a heck of an equation though. Right. Question. I mean. Yeah. Okay. Whew. All right. That's 38. So let's do 39 now. Well, 38 was a doozy. 39. Energy released in one fission of 235 is 3.2 times 10 to the power minus 11. Avogadro's constant is that. What's the power output of a nuclear reactor which consumes 10 kg of uranium-235 per day? So that if you knew how to find the mass of one particle, which was what I emphasized on, right, you would be able to do most of these, right? So firstly, you had to find out U235, what's the mass? How many kg is that? So you can take 235U if you want, right? Or 0.235 kg divided by 6.02 times 10 to the power of 23, right? You can do that. That's the mass of one particle, right? Mass of uranium-235, one atom of one nucleus. Okay? And therefore 10 kg divided by this mass, that will give you the number of uranium-235s, right? Which is how much, by the way? Did you write it down somewhere? No? Okay, I can punch it in as well. So basically it's 10. Because this one calculation, if I want to do this correctly, I will have to do this properly. So 10 divided by 0.235 divided by 6.02 times 10 to the power 23. Right? 2.5617 times 10 to the power of 25 particles. And then you take this multiplied by that. Oh, shoots! I hate them. Options are in watts. So it's per second. So this 10 kg per day. That's not good enough. We need to figure out what's the in each second how much mass was consumed. So these are the numbers in this is the number of uranium-235 fissions in one day. You need to do in 1 second. In 1 second. So divided by 24 times 3,600. So it's 2.9649 times 10 to the power 20, right? Atoms, right, in 1 second. Okay, this is number of fission. So therefore, the total energy will be this number of atoms times that one there. Right, so answer times 3.2 times 10 to the power of minus 11. Right, so 9.49 times 10 to the power of, geez, I have to count this. I can't get a standard format for this. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is your answer. There you go. Okay, done. Oh, whoa, 40? Oh gosh. Well, hey, well, the last few questions are really they are really making you work for it, man. Okay, let's do it anyway. For star X. Okay, so underlying equation is L equals to sigma A T to the power 4. Which is ironic, right? This equation is not even in E5, it's in B1.
But they ask you in E5.
Yeah lah. I know this is in E5 lah, yeah. Anyway, so 10 to the power 4 of L naught, right? L sun is equals to sigma area. So star X is 10R, right? So it's pi 4 times pi 10R squared and then Tx to the power 4. Is that right? Yeah. Then for Y, 10 to the power minus 3 L naught equals to sigma 4 pi, right, 0.1 R squared Ty to the power 4. Then they ask you what is Tx over Ty. Is that right? What the frick, man? Huh? Okay, fine. Wait. 10 to the power 4 divided by 10 squared. Okay? Firstly, 10 to the power 4. 10 to the power 4 divided by... but you know, it's exhausting, right? By the end of this paper, you'll be like, what the hell, man? I still have to do all this shit. 10 squared. What? 100 over... Okay, then 10 to the power minus 3. 10 to the power minus 3 divided by 0.1 squared, so which is 0.1. Then you need to root 4. So 100 divided by 0.1. Then you have to, where am I root? Shift. No. 4. 1000. 5.6. B is your answer. Done. Yeah, okay, awesome. Okay, so anyone with any concept problems throughout the paper here, like anywhere that you got stumped on that you're not sure of and you feel like you need a video, and then you know, maybe like for example this one here, and maybe you need to catch up on this thing here like this. What hasn't come out yet? What Oh yeah, that's way too much. Hmm. Circular motion didn't come out. Standing waves didn't come out. Yeah, standing waves didn't come out. Resonance didn't come out. Mm-hmm. Hmm. Um. Huh? What? Yeah, gas law. You probably need a Carnot cycle, right? Those are the usual suspects for paper two, right? Hmm. 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 Okay. Yo, what's up, Ryan? What's sorry? What? 35. 35. Yeah, no, cause the thing is that the intensity, right? So the underlying understanding for intensity in quantum is that intensity is n over t times the energy of a photon divided by A, right? So this one is like very detailedly explained in in E what E1 no, this is E2. Photoelectric effect is E2. Yeah, this was explained like in quite a lot of detail in E2. Like you probably will have to, watch it to understand it lah, right? Okay. But very quickly, just to let you know, the intensity, right? Intensity is rate of photons times energy of each photon divided by A, right? So they're saying that I change the wavelength is now a shorter wavelength, right? Shorter wavelength, and then I go and change the intensity. I make the intensity a bit higher. Okay, I make the intensity a bit higher. But the current, right? The saturation current up here, it depends on the rate of photons and the rate of electrons that's coming out of the plate, right? The rate. So which means that I need to check the n over t, which is why at first, right, I just drew a higher current. Then the two of them here like not quite, because you need to check this thing here, right? So because I just simply assume that, oh, 1.2 means high intensity, right? 1.2 means high intensity, then it should be higher current one, right? So then I realized, oh shit, no, they're changing the frequency, they're changing the wavelength. So you know what I need to do? I need to write the equation for the new second radiation, the new wavelength. 1.2 times the original intensity, n over t, hc over 0.7 lambda, and then I go and check what is the ratio of the rate of photons compared to the previous rate of photons, right? So it turns out it's 0.84 rate of photons. That means there's less number of photons coming out per unit time, right? Long story short, it means that I use a higher frequency light, but I used a light where it has a lower rate of photons, even though the intensity is higher, right? The energy of each photon is so much higher than the amount of rate of photons that even though it feels like it's high intensity, it's not, right? I mean, it's high intensity, but the rate of photons is not higher, it's actually lower. So you work out to be 0.84, right? Now I'm just saying this on the assumption that you understand what the underlying things are, right? So all these about like this what this intensity is, what rate of photons times energy of photon divided by area, all this, like if it escapes you, you have to watch the video, because that would take me about like 15 to 20 minutes to settle that. Okay, I can show you exactly where it is. So if you go, I mean, I'll tell you where it is now, right? So that you can kind of like watch it like once we. So there's the D and E, right? There's the D and E. Where is it? D and E. I'm assuming it's here. I don't know. I haven't really looked at it in a long time. So this is no. It's E2. It's E2. Sorry, I keep saying it's. Yeah, we have to go look for E2. E2 part 2. Wait, let's see this. Let's see whether this is the case here. Yeah, there we go. Yeah, this one here. Uh, like it's this page, right? It's this page here, right? So everything from this point here, around this point here, right? So a little bit of banter there, right? I don't know. It's like obviously you can see that I'm not really teaching there. You can just skip that part. Okay, but it will be starting from here, right? I will just timestamp this thing, right? And I'll send it to the Telegram chat as a reminder that the So I'll do a screenshot here as well for this. Yeah. Don't worry about it. As in, like, it's just that, I mean, it's gonna take me a while to explain the whole thing. How long would it take? So let me see.
See.
It's about 15 minutes actually. Yeah, 15 minutes. Yeah, 15 minutes. Usually most of the cases are never that long. It's just yeah. We have this one, and then we have this one here, and then I will use this screenshot here. I just kind of like give you an idea of where it is, where this concept is. Yeah, yeah. 35 onwards, those were hella hard questions though. These people are nasty, man. Not even 35, 32 onwards it was hard already. Yeah, 32 onwards it was just like bad. As in, it was already hard to begin with. The concepts were already hard to begin with, but they made the hard. They gave you guys hard questions for hard topics, right? These people are just nasty. That's why I say they're nasty. Usually we don't see IB doing these kind of things, and not like maybe for one question lah. For out the last 8 questions, they consistently gave difficult questions for all of them. Look at that. Look at the amount of work that I had to do. Like, what the heck? Yeah, these people are just like, they're really trying to get you guys. Yeah. But okay, right. So yeah, go and watch it after today's lesson, and then maybe yeah. Okay. What predictions are? What should we try to do some predictions for paper 2? I don't like to do that though. But okay, we'll see. Just maybe more like a reminder, right? Reminder. What? Well, how much? 29.
26.
Huh?
26.
26. Wow. Shit.
So like 10 of them because I read the question wrong.
No! You read the question wrongly for 10 of them?
No, like like the change in East.
No!
Oh, it sucks.
Okay. Kanchong lah, that one is kanchong. Anyway, it's tough lah. I honestly think that is hard. Wait. I'll do this. I'll do this now. Okay, come. What are the things that have not come out yet? They did do. Wait, your CTs in July was D and E, right? Your CTs in July was D and E, right? Yeah, D and E. Velocity selector already came out, right? Yeah. Okay, anyway, so kinematics, what hasn't come out yet? Projectile motion. Right? If anything, projectile motion hasn't come out yet. No, yeah. Projectile motion hasn't come out yet. So you can start listing this down already, right? Projectile motion. Then for A2, forces and collision, circular motion haven't come out yet. Collisions haven't come out yet. All the momentum concepts, right? The helicopter, the water hose, the water rocket, the two objects colliding and all that, all not out yet. Work energy power somewhat, right? Wasn't there some yeah, the GPE and the KE question, yeah, that one's done already. Rigid body mechanics, only the angular momentum, the conservation of angular momentum. Huh?
No, like there's angular acceleration question also.
Yeah, actually I think this one is done already, Yeah. Yeah, I think this one's done. Relativity, I think it's gonna come out.
Yeah.
One random thing is gonna come out. So the other day on Sunday, I don't know, maybe it was something that I subconsciously didn't realize, but I now understand that IB makes it a difference where they ask you the distance between events versus the length of an object. So if it's the length of an object, right, there's length contraction. But if it's distance between simultaneous events, right, that one is a length extension. Like length will be longer. Yeah. So that was the thing that I was doing in the in on Sunday, and I realized that there seems to be something like common. There's a common trend to it already. The spec paper also had a question on that, right? where instead of them doing length contraction, they did extension, right? There was a distance extension. You want to think of it as length contraction but distance extension, right? Distance between two events, right? Yeah. So relativity is gonna be the one of those things, right? Pretty sure that that will be the case. Thermal energy transfers, right? If you remember, B1 is a mixed bag. B1 is a mixed bag of like 2, 3, 4, right? So B1 has conduction, convection, radiation. Then you got your Stefan-Boltzmann's equation. You got Wayne's displacement law. Everything is there, right? Haven't really touched yet. Then you got your greenhouse effect. Greenhouse effect. The atmosphere one, yeah, but you didn't get the one where they most of you always ask me why is it divided by 4, right? Why always divide by 4? That thing, right? Yeah, that thing is inside there. Then you got your gas laws, which is your PV equals nRT and all the equations, right? PV equals nRT. The two chambers actually, the two gas chambers actually is sort of like came out already, right? Okay, so not like the thermodynamics. Thermodynamics is what? Oh, PR and RQ, right? That one, right? Okay, so the only thing that hasn't come out yet for thermodynamics will be the Carnot cycle, right? The Carnot cycle and the efficiency of a Carnot cycle versus the efficiency of a heat engine, normal heat engine. So current in the circuit seems like it's done, The 1B had internal resistance, and then you had some circuits equations. I would think, I mean, if anything, it would be the potential meter, right? If it's B5, it's potential meter. Okay, SHM. SHM, you have SHM, nothing there? Yeah, you got a mass spring oscillation, the energy of a mass spring oscillation. So probably not. If anything, it's vertical mass spring, right? If anything, this like vertical mass spring is pretty much the next thing. Wave model is just your general waves. Yeah. Oh, actually, we had some waves, right? Yeah, some particles and waves and all that. Wave phenomena. This thing is the biggest topic, right? So you got your reflection, refraction, double slit, single slit, diffraction grating, modulation, all of that, all inside here, right? All the equations inside here. Nothing very obvious for diffraction has come out yet. So diffraction grating is one of those things. Single slit came out already, right? Somewhat. Okay. Yeah. So diffraction grating, if anything, right? Diffraction grating and refraction already done already, right? Unless they want to ask about TIR, right? Unless they want to ask about TIR. So TIR and diffraction grating haven't come out. Only the last question there. Yeah, it's not. Standing waves and resonance. Nothing came out of this yet. Nothing came out of this. I just forwarded because someone asked me about the EJC question that I sent out, right? Resonance, right? Yeah, about this one here, right? Someone just asked me about this one here, so I went through this one with my JC class, right? Yeah, maybe you want to take a look at that, right? I'm pretty sure that it will be quite interesting for this thing to come out. Yeah, yeah. Resonance, Doppler effect, nothing came out yet, right? Doppler, nothing came out yet. Wait, so the Doppler. So maybe the other thing is the EM Doppler. EM Doppler haven't come out yet. All right, so we have the G field. So all these things here, wow, they really made this part here really tough, huh? Right, your MCQ 32 to 40, right? 32 to 40, they made it really hard. All right, that's tough, man. I would say that for this paper, right, if you can get anything above 29 is really quite good. Right, legit, yeah, if you can get above 29 is very good already. Because of the last few questions. Those last few questions, right, those are like yeah, tough, man. Okay, G fields. G fields. Orbit, escape KE, right? Orbit and escape KE, orbital energy, losing energy during orbit, all these things, right? D2, E fields and B fields. Force between wires, magnetic force on wire, magnetic force on magnets, magnetic force on charged particles, velocity selector was tested, right, CT? Huh? It was, right? Yeah, so I don't think velocity selector will come out again, right? Okay. Yeah. So these two things here, motion and electromagnetic fields. In induction, no? There was a generator question there. Generator question. The only one I can think of that will be challenging for induction will be you have a falling rod, right? The rod is falling and then it's falling at terminal velocity. So the weight of the rod is balanced by the opposing force due to the F equals to BIL, right? That thing, right? So that concept I went through before. Structure of atom. If anything is that Rutherford deviation, right? The size of the nucleus and all that. But I think we went through. I think they also tested that already in CT, right? They give you the graph, right? Yeah. Quantum physics, photoelectric effect, Compton scattering. Hey, wait, were you tested Compton scattering in CT? Ah, Compton scattering. Okay. Oh, Compton scattering didn't come out at all, huh? Compton scattering is E2. Yeah, Compton scattering is E2. Yeah. What? Electron diffraction, right? Wave particle duality, right? Quantum physics there. And then we have radioactive decay, which is alpha, beta, gamma. This one not too big an issue. Probably the probably mass probably energy just watch out, they're probably gonna give you like some binding energy shit again. So either they give you mass or they give you binding energy, right? Then they ask you to calculate the binding energy again. But it came out of CT, right? So I'm guessing it's hardly likely lah, right? Yeah. Then you got fission. Fission is uranium-235 fission. Nuclear reactor, they asked about this really also, right? Control rod and all that, right? Yeah, so not likely as well. Fusion, probably stellar evolution. Probably because that one has not touched yet, right? Yeah. So the life cycle of the sun, yeah, the mass of the sun, does it become a white dwarf or does it become supernova? That sort of thing, and then draw the HR graph, like the position, like where the evolution goes into, right? Trying to hit all the things. So all the things I mentioned is like trying to figure out like whether or not, yeah. So with that, maybe you can look at the paper tools and try to catch all those parts, right? All the different parts. Okay, hang on, All right. So at this point, I think what I'll do is I'll just check on whoever has any questions, right? Whoever has any questions. Wait, Q&A room, right? This one, Q&A room. So someone was asking these two questions here. I'm not too sure what this is all about. Atmosphere exerts a small viscous drag force on the satellite. Outline how the total energy KE and GP change for the satellite during one orbit around the Earth. Why one? Why need to be one orbit? Okay. But I did do this before, right? Kind of like we'll just just tell you where it is, right? Let me just show it to you. I'll go through it very quickly, but it is somewhere in D1. So we go back to D1, maybe somewhere around here. Part 2, maybe. Part 2. Orbital energy. No, this Kepler's laws. Oh, Kepler's laws, guys. Kepler's laws. Did we? Not yet, right? Kepler's laws have not come out yet. Yeah, so you may want to target a bit of Kepler's laws. Especially the comet example I gave. So I gave this comet example here, right? See whether or not it's useful. Yeah. Right, see whether or not this thing is useful here. GPE. Oh, so this is me teaching GPE, and then I went through all these different GPE stuff. And then I think I have to look at part 4 now. Yeah, D1 was a pain, man. D1 was so long. It went into Chinese New Year, right? I think this was Chinese New Year. That's why I'm wearing my Hawaiian shirts. This is escape speed. Yeah, okay, right. So this was the wait, no, hang on. Wait, what am I doing? Why do I increase the speed? I wanted to decrease the speed. Why do I go through an example where I'm increasing speed? That's so annoying. No, I wanted to do in decrease speed. Shit, that means I didn't do the decrease speed version. I did the increased speed version, which is lame. I usually don't do increased speed. Okay, I'll do the decreased speed now. Okay, all right. So that's in my video. This was how does a satellite go into a higher orbit, right? In the question that's being asked inside the Q&A room, this one here is, how does like viscous drag force on the satellite? So what happens to the energy during the orbit around Earth? Okay, so we have to go through that now. How come I didn't go through that? Okay, anyway, so Earth, right, and satellite, right? We have a satellite. So the satellite is going around the Earth, like this, orbiting around the Earth. Okay, this dotted line was the original orbit. If nothing happened, it will be original orbit, right? And then there's some disturbance here. So a bit of debris, for example, debris. Okay, what did the question say?
Viscous drag.
Viscous drag force. Okay lah. So some basically something to block its path lah. Okay, right. So this satellite will fly. Okay. Sorry. Will head towards. Alright. It will head towards this debris here like this. Okay. This is the part where some students get very confused by. They thought that the satellite needs energy to orbit. No, it doesn't require energy to orbit. It has orbital energy, but it doesn't need energy to orbit. Like there's no rocket boosters that keeps on making orbit. This part here, some students get very confused because they think that once this satellite hits this thing and lose energy and slow down, they think that this object will start drifting off into space, right? That is absolutely wrong. The satellite cannot drift off into space, right? Because to drift off into space means that you have to have enough energy to escape Earth's gravitational field. Don't forget, Earth's gravitational field is always trying to pull you back in. So if you lose energy here, the first thing happens is that it will cause you to drop to a lower orbit. Yeah. Okay. So this thing here, this thing here goes down, right, like that, right, and then the satellite here like this. So number one, this obstruction, or rather this viscous drag, right, viscous drag causes satellite to lose, right, total energy, right? It will lose total energy, okay, right? Causes the satellite to lose total energy, right? Then number two, the satellite will fall to a lower orbit. Okay, why is that? Because for orbital energy, if you remember the graph, for orbital energy, the graph looks like this, right? The graph looks like this. Okay, the graph looks like that. Sorry, something like that. Okay, I mean, yeah lah, you get what I'm saying. Wait, hold on though. Kinda do want to make it a bit nicer. Right, so yeah. The top graph is KE, the middle graph is total energy, and the bottom graph is GPE. Right. So if you obstruct the satellite, it will lose total energy. So if it loses total energy, you look at this here, right? So it was at a higher distance, R2. It had this amount of total energy, but the obstruction causes it to lose total energy, so it will drop to a lower total energy. Right here, this is like, and therefore it will fall to R1. Okay, so this will be R1. Right, previously it was R2. Okay, so it will fall to a lower orbit. R2 fall to R1. R2 fall to R1. And then this satellite will continue to orbit, but it's at a lower orbit. Okay, it will continue to orbit, but it's at a lower orbit. So we'll just do this. Right, so now it's a smaller orbit now, lower orbit. Okay, but in doing so, right, so the irony of it is, at its lower total energy orbit, right, at the lower total energy orbit, if you check the KE, the respective KE and GPE, right, it would appear to be like, oh, the KE actually increased. The KE got more, right? The KE got more, right? That means it orbits a smaller radius at a higher speed, and the GPE is lost because you fall towards Earth, you lose GPE. That's for sure. Okay, so the answer to that question is, right, and the viscous drag causes the satellite to lose total energy, right? The satellite will fall to a lower orbit, right? The total energy cannot be recovered already. It's there, right? But in doing so, the KE and the GPE will increase, right? So the point 3, right? KE and GPE, KE increase, sorry, KE increases, GPE decreases. Sorry about that. Yeah, right. So KE increases, GPE decreases. So you lose total energy, you gain KE, but then you lose GPE, right? Yeah, there you go. So that's the answer to this. Okay, so that's for that one. I think the album there was a combined one. We have another question, alpha emitter. Alpha emitter question. Looks like specimen paper for both. So yeah, this one is your, yeah. This is kind of like a bit of the bread and butter of IB. IB loves to ask this question. Like you see, like the person. What who? Mm-hmm. 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 What? Sorry. Okay. Hold up. Hold up. Hold up. Okay. That's why I love it when we are a bit more explicit about it. GPE becomes more negative. So you lose GPE. GPE becomes more negative. Okay? Yeah. So yeah. Because if for this satellite to escape, like I say again, for this satellite to escape like the Earth's gravity, right? Like basically this guy must be able to get GPE 0, which is technically the maximum GPE. 0 is maximum. The more negative you go, the more GPE you lose. Can I? Okay, then I got this decay question here. Smoke detector. Oh, there you go. Smoke detector. It's a smoke detector question. Did I not go through this before? I forgot already. Anyway. Okay, we got smoke detector. You know that it uses alpha particles. This is pretty much the only one use that we have for alpha particles. Okay. Um, there's an americium source and it's coming out. Okay. And the electrodes are the detectors. So when americium touches the electrodes, right, there's a battery here, the sensor will be like, oh, as long as there's alpha particles touching it, it will generate a current. If the current is consistent, right, then then nothing will go off, right? The smoke alarm will be like, okay, everything's fine, right? The whole idea of how this works is when smoke starts to rise and the smoke comes up here like this and it blocks all these alpha particles, then the electrodes don't detect the alpha particles anymore, right? Then the current sensor will be like, okay, you know what? I'm not detecting any alpha particles anymore. I'm not detecting any current anymore. I'm just gonna sound off the alarm, right? That's how the fire alarm works. Okay, so something like that. I mean, in more details, right? Alpha particles ionize the air. The ionized air, one positive ion, one electron. So one positive ion goes here, one electron goes there, right? The electrons and positive ions creates the current, right? Creates the current. I mean, I'll show you here now. Sorry, because I explained it in a very simplistic way. I didn't realize that they were so detailed about this. Okay, so your alpha particles will create ionized air particles. Ionized air particles. You have electrons, and then you have the positive. Right, I'm just gonna give you O2 lah. Let's say it's O2 plus, okay? O2 plus. This is a positive ion, right? Positive oxygen ion. Like where do they go? So the electron will travel over to here, hit this plate, and the oxygen will hit this plate like that. Right? Do you know why the electron travel here? Because this side here, the battery is positively charged. The other side is negatively charged. So the electron go here and the oxygen go there. Okay? But here's the other thing. I think I just went through this on Monday with my year fives, right? So some students are like, don't these two traveling one this way and traveling the other this way doesn't it cancel the current out? Actually, no, right? You see, I'm gonna draw this for you. You see the electron moving this way, the electron going there, and then the positive ion moving over here, right? Do you realize that in doing so, if the electron travels to the right, the current points to the, sorry, if the electron points to the left, the current points to the right. If the positive ion moves to the right, the current points to the right. So technically speaking, the total current due to the negative ion and the positive ion is actually the sum of these two currents, right? So it's like double up. It's not even cancelled, right? It's doubled up. So the total current is like this I plus I. Okay, so let's try to understand that because I think they are asking for that. Yeah, I think they are asking for that. Yeah, right. There we go. All right, right. Okay, can. So decay constant of americium is 5.08 times 10 to the power minus 11 per second. Chamber is 0.1 meters in each dimension. This sounds like a tough question. Initial activity is 42,000 becquerels, schmeckerels, right? So 42,000 becquerels. 33% emitted enter chamber and form an ion pair. So times 0.33 times 0.33, how much is that? Let's work it out. 42,000 times 0.33. I get 13860, right? Electrons and 13860, right? Sorry, my sensor there is a bit. I haven't calibrated my sensor on that side. Sorry. 60 air plus. Okay, so there's a ionized air molecule there. So we get like two, right? We get two. So this amount of electrons and this amount of ionized air molecules. Each alpha particle has an initial Ke of 5.5 MeV. Energy required to form one ion pair is 15 electron volts. Damn. Okay. So which means that how many ionizations can you get? No, yeah. Yo, what? Oh, how many ionizations can you get from one alpha particle? Number of ionizations from one alpha. Just one alone, man. 5.5 times 10 to the power 6 divided by 15. Yeah. This is the spec paper question. You want me to print out for you? Hang on. Spec paper, this is no, this one's the SL question also. How, yeah. Yeah, I know, right? Specimen 2025, specimen 2025, paper 2, HL. So, this is 10, 11, 10 and 11. Yeah, wait now. Let me print out for those who are here first. Don't worry. No, don't worry about it. Okay, I cancelled this part here first because I realized that I didn't have to do that. So I cancelled this one first. All right, I cancelled this one first. This part here. All right. So basically, I have 13860 alpha particles per second that can go on and do ionization. 13860 alpha per second that can ionize. right? So 13860 alpha per second that can ionize. Then understand that from each alpha particle, you can ionize this many pairs. We have 5.5 times 10 to the power of 6 times 10 to the power of 6. I get, oh, then answer divided by 15. I get, oh gosh, what a weird number. 3666.7, right? 3666. 7 ion pairs. Okay? What time, 3:30 ah? Oh shit, okay. 3:30. Wait Then total Q per second that you can get will be 13860 times this number 366667 times 2 times 1.6 times 10 to the power of minus 19. Right. This is the very difficult one. So understanding that 33% of the alpha particles can do ionization, right, can form an ion pair, right? So 33% times this is 13860. Okay. Then based on the next information, they say that each alpha particle has 5.5 mega electron volts, but then energy to form one ion pair is only 15 electron volts. So technically speaking, the number of ionization, right, the number of ionization is from one alpha particle, right, just one, each alpha particle, right, is this amount. So is this weird number, right, 3467, right, 366667, right, ionizations that you can do, right, so ion pairs that you can make, right, yeah, you can make this amount of ion pairs. So the total charge, what, sorry? Wait, let me check first. Let me check first. Yeah, okay. Then the total. Oh shoots. Okay. You know, I multiplied by 2. You know why? I multiplied by 2 because I was going with one electron and one positively charged air molecule. So the current is going this way, like that, right? But then the question says maximum current due to electrons only. Yeah, these people, make up your mind, man. You want to make it hard, just make it all the way lah. So it's only due to the electrons, only. So yes, don't need the times 2, right? Because I assume that you're talking about like one electron and then one positive ion. So only due to the electrons, so I cancel away the times 2. So 13860 times this, then times the charge. And this is per second, right? That's current. So that's the maximum current that you can get. How much is this? 8.13 times 10 to the power of minus 10, that's all. Minus 10 amperes. That's pretty weak, man. But yeah, I guess, yeah, there's not enough zeros, right? But yes, I think this should be the answer. Is that the answer? Cassandra? That's the answer, yeah. So yeah, I mean, what? Sorry? Oh, okay. All right. And there we go. So I thought it would be like double the current because like because I know the electron will travel this way, positive ion will travel that way, so the current will be doubled. But yeah, they only ask for electrons, so it's only times one. Anything else that you want me to clarify? Okay, if not, you can ask questions still, but it's just that I have lessons until 9 o'clock tonight. So if anything, I can only reply later. Can I'll try my best lah. So same thing, just drop it in the tally. Just drop it in the tally. Everyone's anonymous anyway, so I really don't know who it is. And then I'll answer you later. Okay. HL, I'm done. It's SL's turn soon, 3:30. Right. If anybody has any other questions, let me know. Otherwise, I think you can actually get most of the information from the shared drive. Do take note of the the kind of like we're trying to spot the questions right just now. Although I don't really believe in it, but I guess you can. You can. Yeah, look through all the questions and then just look at the videos lah, I guess. If you want continue practicing, what you can do is this. For all the topics that I've mentioned, right? All the parts that I mentioned, maybe what you want to do is you want to just go in to the paper 2 and then yeah, go into the paper 2 and then start looking for questions like the yearly November papers. There's a few things that yeah. Run through the syllabus. Run through the syllabus. I would say run through the syllabus. I think that's the best you can do, right? And then see which ones are the ones that's still not tested yet. Yeah. Yeah, like things like Compton scattering. Kepler's third law, actually. Kepler's third law is a pain, right? Kepler's third law. Yeah, relativity. Yeah, pretty sure something like this will come out, right? If you see the Q&A room, I think on Sunday. No, not on Sunday. The other day. Where is it? Shit, I can't remember where I left it. This one here, yeah. So this one turns out to be this one turns out to be length extension. Yeah, this turns out to be length extension. No, this is not it. There was an event one. I can't remember where it was. It was somewhere. It was in one of these things here. Okay. If anything you have to text me, right? I have to see the SLs now. So those online, thank you very much, guys. Bye bye. Thank you. Bye guys. Bye, Jetro. Thanks, man. No? But okay. Bye bye. Take care. All the best for tomorrow. Don't worry about the score. The last 8 questions are damn freaking hard. They're damn hard. It's like down here I breathing, I cannot already. It's like I'm like starting from 33 onwards, it's like the math is like whoa, and then after that another math. It's just all freaking math after that already. Yeah, it was like what the freak was going on? Like I was